So I can't hear you. My sound is off. All right. Can someone say something?
Yeah, Mr. Reeves, I just wanted to tell you that Sav texted me and said she's having Wi-Fi issues right now.
Sound's still off. Okay. All right, try that again. Owen.
Sav texted me and wanted me to tell you that she's having some Wi-Fi issues right now.
Wait, who was that?
Sav. Savannah.
Sav. Got it. Sorry. All right, what do we got? 4. We got 12, 13, 14. And Savannah made it work too. Okay, so all of you got emails this morning telling you what your grades were on that last quiz and also what your current grade is in the class. I hope you found that helpful. I know that they were like short and to the point. Everyone kind of, I just did a Control-C, Control-V and changed the numbers. So pardon me for not being like really crazy and discussive and all that, but hopefully you found that good. I graded those quizzes relatively leniently, I will say, with a reasonable amount of possible extra credit in there. So hopefully that helped people out. And hopefully that answered a lot of questions. I know that a lot of people have been asking me what their grades are in the class and everything that's going on. So there it was. Sorry for the late start today. I was in my office hours with another couple of students and we went a little bit on the long side. And then my computer decided it would shut off, which was my bad for not having it plugged in. Okay, so let me take a look. Caught me off guard on what we are covering today. Today should be section 12.2. Okay, give me 1 sec. Let me see if I can just grab the paperwork. Slightly disorganized over here, but let me see if I have. Okay. Nice. Got it. All right. Boom. Got it. Let me join up on this. I'll do boom, join. It's probably going to echo at us for a while. Okay, and we're back. Can you guys hear me still? Got a nod in there, and we got both my cameras working, and let's get into some Sigma notation. I like this stuff. I think it's kind of neat. So here we go. All right, this is the Greek letter sigma. It looks like an E, but it's actually supposed to look more like an S. If you are touring a college campus and look at the fraternity SAE, that is their S, that's sigma. It means the sum of things. It will morph once you get into calculus into something which looks like that, looks more like an S, but that is a story for another day. What it is it's just a short way of saying, hey, add up a bunch of stuff. So the key word there, of course, is add. So what stuff am I adding? I'm adding every integer value where k starts at 1. So this is really my starting point here. Up until k equals 4. So that is my ending point here. Any of you guys do computer programming? I saw a slight wave. Jacob, you did computer programming this year? Awesome. Yeah. Awesome. So I used to teach C++. I taught Java a little bit at our school, but I'm more of a C++ guy. This looks like a for loop or a while loop. You know, while x is less than, in this case, k is less than or equal to 4. All right, so I add all these up, starting with k equals 1. So I have 2 to the first plus 2 to the second plus 2 to the third, and my last one is going to be 2 to the fourth. I do include the last one, and there it is. Okay. So this turns out to be 2 plus 4 plus 8 plus 16, and the whole thing should be like 30, I think. Is that correct? Yeah, equals 30. Okay. So it's just a quick way of saying add all those things up. Okay, over here, and by the way, they're saying expand, so technically they didn't ask what it equals. So if you're looking at these and going, oh my God, that is super ugly, I don't want to add those things up, technically we don't have to. So this one is going to look like 1 squared plus 2 squared plus 3 squared plus, I'm going to put the dot, dot, dot. What's my last one going to look like?
K squared?
Not k squared. K is what we call the dummy variable.
N squared?
N squared, yeah, absolutely. N squared. All right, and this is kind of the same thing here. This one is going to look like 1 factorial over 2 plus 2 factorial over 3 plus 3 factorial over 4 plus dot, dot, dot. My last one is going to be n factorial over n plus 1, whatever that happens. Strange that they gave us 2 of them with n's. Oh. Okay, so algebra seems not about doing things forward, but about doing them backwards. So let's take a look at example 2, and we're going to do this thing backwards. We are going to now write this as a sigma notation. And by the way, there are an infinite number of correct answers to this question. I'm just going to do the easiest. I'm going to start k equal to
1,
1. I'm going to end when k equals
100,
100. And in terms of k, each of my terms just look like k. That one's not real hard. But for the fun of it, I did say that there are an infinite number of correct answers here. If I put this on a test, this is the one which I would expect you to give. If I were writing an answer key, this is the one that I would put in the answer key. But there are plenty of other things which I would give you full credit for. What if I did this? Sigma k equals 10. Huh. Now where's it going to end?
1,000.
Not at 1,000. I doubt. I mean, unless you have a
100,
not at 100.
10,
I think it's going to have to end at 109. What are each of my terms going to look like? Are those two things equivalent? It says k minus 9 in parentheses. So here, what's my first term? When k equals 1, well, what does k equal? 1. When k equals 10, what does k minus 9 equal?
1.
1, absolutely. When k is my next number, 11, then I'm going to get a 2. When k is my last number, 109, What does k minus 9 equal?
100.
100. Absolutely. So are these two things equivalent? Yeah, they are. Is one of them a whole lot more obvious than the other one?
Yeah.
Yeah.
When you're like,
Mm-hmm.
because how do you know immediately if you like take the, what's the name of like the symbol again?
Sigma.
Like if you take the equation with the sigma and then how do you like immediately know how to turn that into the next, like what it's equal to?
Well, there's no one-off answer to that. So it's just like we did last time we met, which I believe was Thursday. It's kind of a continuation of that where we were looking for patterns, that kind of explicit formula. So like, what are all these numbers? 1, which believe me, there's an easier way to write. 1/3, 1/9, 1/27. I'm thinking of this as 1 over 3 to the 0th plus 1 over 3 to the 1st plus 1 over 3 squared. Does that make some sense? Okay, so now let's write it as a sigma. I think I'm going to want to start k equals,
Move it down.
yep. Fine. K equals 0 seems like my my smart choice. And over here, I could do n minus 1. And these are all the sums of 1 over 3 to the k. Maybe there's a better way of writing this one. I'm going to put an or. If I say start at k equals 1, where should I end this time?
N.
At n. You got it. And what should all my terms look like?
1 over 3 to the k minus n, or k minus
K
1.
Minus 1.
Minus 1. Beautiful, beautiful. Very solid. I like that. Okay. This one is hard until I realize that 1/2 should probably be written as
3/6.
totally. So if I write it as 1/4 plus 2/5 plus 3/6 plus 4/7 plus ... 10/13, I think it's not too hard. This is going to be the sum from k equals, what's the obvious starting point?
Equals 1.
I think so. If you do 1, where's it going to end?
10.
10, totally. What do each of my terms look like?
K over k plus 3.
That's what I wanted to hear. K over k plus 3. Again, I'm going to put an or because I think there's another pretty decent one. This time I'm going to start k equals 4. Where am I going to end?
13.
13. And what is each term going to look like? Help me think.
1 over,
Don't think 1 over. Isn't that equivalent? Y'all like it a lot or no?
where do you like get that from?
Wait, no, because then
Where do
if you do it for 4, wouldn't you get 7 over 4?
Oh, sorry, hang on. K
Minus-
minus 3. I kind of did a double negative in my head. Sorry about that. A minus 3. Does that make sense?
Mm-hmm.
Okay. And Savannah, you were asking where I got that from. Well, notice that these numbers just go 4, 5, 6, 7, blank, 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 13. I'm saying, oh, start when you got 4. And this one ends at 13. Oh, thank you, Owen, for muting that. And how are these numbers related? They're always 3 less, because it goes 1, 2, 3, 4, ... up to 13.
But how is that 3 less if it's going 1, 2, 3, 4?
It's 3 less than the denominator, which is going 4, 5, 6, 7.
Oh. Oh, okay. Okay.
Right. A lot of these rules you will continue to use when those things which look like E's and are called sigmas start looking more like S's in calculus. So let's take a look. So if every term is being multiplied by C, well, then I can factor it out. So for example, if I had sigma from K equals 1 to 10 of K, or 2K, then I would have 2 plus 4 plus 6 plus 8 plus blah, 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 plus 20. Or I could factor out that 2, and I would just really have 1 plus 2 plus 3 plus 4 up to 10, and then I would double it in the end. So this equals 2 sigma K equals 1 to 10 of K. Doesn't matter where I put that constant. Okay. These two rules, I think, are the same thing as one another. If all the terms add, then you can just do 2 different sums. Or if all the terms subtract, then you can just do 2 different sums.
Is it kind of similar to like what we were doing in the last unit, where when you have like log of A, B is the same as log of A times A plus log of B? Is it kind of similar like that?
Yeah, I'm kind of going with no, because in logs, the additions became multiplications and stuff like that. So I don't actually see a kind of one-to-one thing. But maybe you're seeing some connection that I'm not. It's possible. This last one, I feel like they did a little bit too easy for us, or too simplistic. They are really just changing that first term. So they're saying if you want to change that starting point by a little bit, you can do that just by removing 1 or so of the terms. Okay, these formulas I'm going to give you. You do not have to memorize them. You will, on the quiz, on the test, I think we only have a test, not a quiz. On the test, I will give you these formulas. You do not have to memorize them. Let's see how they work. So example 3A really is this guy. Notice that 3 does not depend on K. 3 does not depend on K. If K equals 1, then what does 3 equal? Easiest question anyone's going to ask you all day long. What does 3 equal? 3, yeah. If K equals 2, what does 3 equal?
3.
How many 3s am I going to have here?
20.
I'm going to have 20. I'm going to have 1 when K equals 1, when K equals 2, all the way up to 20. I've got 20 of those 3s My answer is just 60. And that really was that first one. C just happened to be 3. Does that make sense? I hope so. Okay. This one, I'm going to be a little sneaky. I'm going to use that second rule under properties of sequences. I'm going to rewrite this as the sum from k equals 1 to 5 of 4k plus the sum from k equals 1 to 5 of 9. Oh, okay. I know what this is. It's just 5 times 9. This, the 4 can come around in front. So this is 4 times the sum from 1 to 5 of k, which I can use this formula for, but it's not real hard. I can do this on my fingers. It's 1 plus 2 plus 3 plus 4 plus 5. 1 plus 5 is 6. 2 plus 4 is 6. And so I'm at 12 plus that 3 is 15. And I get 105. However, let me do that same problem another way. There's another formula which I want to share with you guys, which is not on the sheet. Okay? And this is for the sum of linear terms. Okay, so anytime it looks like mx plus b. This formula comes with a story. You guys want to hear a story? Story time? Yes, yes. Okay. So Euler was a young lad, and there's some embellishing in the story. I doubt most of this happened, in 3rd grade. And he showed up at school and his teacher was hungover. Teacher had a rough night partying, whatever it is that, that 3rd grade teachers do, and did not want to deal with loud, noisy 3rd graders. I understand. I do not want to deal with loud, noisy 3rd graders either. I much prefer my yawning, tired as all heck 9th graders here. So the teacher devised this plan. Said, all right, this is what you are going to do today, class. You're going to add up all the numbers from 1 to 100. I'm figuring, all right, it's going to take them, I think Connor's heard this one before. It's going to take you guys a long time. The first 2 people aren't probably going to end up with the same thing. And then I can tell them, oh, go check your work, see who's right. You know, this is going to be hours. Anyway, Euler said, well, all the numbers from 1 to 100. What is, and this is where I'm going to need you guys to play along, what is 1 plus 100?
101.
What is 2 plus 99?
101.
101. What is 3 plus 98?
101.
101. What is 4 plus 97?
101.
101, absolutely. How many pairs do I have which add up to 101?
50.
50, exactly. My last pair would be 50 plus 51. They add up to 101. So I've got 50 101s. What is 50 times 101?
505.
Add a 0 at the end of that one. 5,050. And that's the answer. Boom. Euler was done in a matter of minutes, if even that long. He handed it in. He got yelled at because the teacher, hadn't even bothered to figure it out on her own. And and so we have Euler's method. And let me show you how it works for other ones. This is the formula. The sum of n terms is equal to my number of terms divided by 2 times my first term plus my last term. Okay, so in this case, how many terms am I talking about? There are 100 terms. I'm dividing that by 2. There's that 50. And my first term was 1. My last term was 100. This is 101 times 50. 50 times 101, and I get 5,050. Let's apply it over here because this one's linear. How many terms do I have in this bottom problem?
2.
Not 2.
5.
5, yeah. Start with 1 to 5. So I've got 5 over 2 times that first term. Okay, that's when k equals 1. So my first term should be 13 plus my last term. That's when k equals 5. And I get a 29. 13 plus 29 is 42. Half of 42 is 21. 21 times 5 is 105. Did it work out for us?
Mr. Reeves,
Yeah.
can you explain how you got 13 and 29 again, please?
Yes. 13 is my first term. My first term is when I plug in k equals 1, my starting point. 4 times 1 plus 3.
Okay.
There's my 13.
Yeah.
My last term plugged in 5.
All right.
Okay. I'm not going to put this too far away because I am certainly going to need it for these things. This is not linear, so that trick will not work. But I can split it up and go k equals 1 to 5 of k cubed plus, well, what is this last little bit really going to be?
15.
I think I heard a 15 in there, yeah. 5 3s. All right, well, how am I going to do this k cubed business? We've got a formula right here. Okay, so I am looking at this formula and I'm just writing it down. We've got n times n plus 1 over 2, and that whole thing squared plus 15. Well, I know what n is. This is 5 times 6 over 2 squared plus 15. 5 plus 3 really is 15. 15 squared is 225. 225 plus 15 equals 240 as my final answer there.
Mr. Reeves, I'm assuming you got the 15 from multiplying 5 and 3.
Yes.
Okay.
If you're doing n and n plus 1, one of them is always going to be even. Divide the even one by 2, because an even number is divisible by 2, and multiply by that. All right, splitting up this guy, I can do it in any number of different ways. I think I'm going to do it this way. K equals 1 to 10 of k squared. And I can use my formula for that. Plus the sum from k equals 1 to 10 of negative 4k plus 12. Okay. I'm going to use Euler's formula over here, and I'm going to use the formula out of the book over here. So my formula out of the book, and I'm just writing it down from the previous page, n times n plus 1 times 2n plus 1 over 6 plus, and this is Euler's formula again, n over 2 times my first term plus my last term. Okay, gonna fill in some stuff. 10 times 11 times 21 all over 6 plus n over 2 is 5. Maybe I'll just write 10 over 2. My first term is what I get when I plug in k equals 1. I get -4 plus 12. I get 8. Plus my last term is what I get when I plug in 10. I get -40 plus 12. Looks like a -28 to me. All right. Making life easy on myself, I'm going to do some reducing. 6 is really 2 times 3. 21 is 7 times 3. And 10, of course, is 2 times 5. So that 2 and that 2 go away. That 3 and that 3 go away. I'm left with 35 times 11. That should be 385, I think. Plus 5 times -20. We get 285. Are we okay with this? Feels like we're going relatively quickly, but smoothly.
Mr. Reeves,
Yeah.
can I ask, why does n times the quantity of n plus 1 times the quantity of 2n plus 1 over 6, why does that work? I don't understand that.
That is the best question I've heard today. Why it works is a hard proof. And honestly, in the 7 minutes we have left, I don't have time to do it. But I've got office hours the rest of the day. If you want to pop in, I will walk you through it. If you just want to see whether or not it works, let's give it a shot with some Excel spreadsheets tomorrow. Or I can try to prove it in some of my rare free time, which I might have today. Unfortunately, one of my colleagues needs me to run out to school after school today. So I'm going to lose a couple hours there. But I can try to prove it for you. I remember that one not being a hard proof and the k cubed one being pretty difficult to prove, but they are provable. So great question. And believe me, that makes me think, yes, I'm talking to a mathematician. When you look at a formula like that someone threw in your face and are like, yeah, why does this work? You know, that really is what it's all about. Let's see. Oh, Aaron, looks like you have a question too.
For C, how did you get the 15?
How did I get this 15 at the end here?
Yeah.
Well, remember, it was 3 every time around. How many times did I go? I went 5 times.
Oh,
So
okay.
really it would be the sum from k equals 1 to 5 of 3. Well, 3 is always equal to 3. So if I have 5 3s, I've got 15. All right. For the sake of time and efficiency and all that, we aren't necessarily going to do these out in their entirety, but we are going to set them up. What I'm going to do, notice that this one goes from k equals 4 to 24. I am going to say that this equals the sum from k equals 1 to 24 of this 2k cubed business minus the sum from k equals 1 to 4, to 3 of this 2k cubed business. Does that make sense?
Why is it 1 to 4 or 1 to 3, not 1 to 4?
Because I don't want to subtract off that 4th one, because that one is going to be there. Right? And so I can write this as 2 times the sum from k equals 1 to 24 of k cubed. And I can do that. I can use my k cubed formula. Minus 2 times the sum from k equals 1 to 3 of k cubed. And again, I can do that. I can use my k cubed formula for that one as well. Okay. For sake of time, we're not actually going to do it, but so it goes.
In class.
I hear someone, but it doesn't look like they're talking to me. By the way, guys, mustache, the girls, my girls, as in like my wife and her sister and all that, hate it. You guys and girls, the class.
I like it.
I got one like.
I like it.
It looks good. Looks good.
Yeah, I like it.
Nice. You guys are either good at line or, as I said, my wife absolutely hates it. All right. Thank you for that. Over here, I'm going to kind of do the same thing. I'm probably going to say that this equals the sum from k equals 1 to 40 of this whole mess, k squared minus k. And then I am going to subtract the from k equals 1 to, what's going to go on the top?
11.
11, absolutely. Don't want to subtract off the 12th one because it is there, of k squared minus k. This I'm probably going to break into 2 ones. So I've got sum from k equals 1 to 40 of k squared. And I can do a minus the k equals 1 to 40 of k, and minus the sum from k equals 1 to 11 of k squared. Yes, yes, yes. And plus, because I'm distributing that negative sign, the sum from k equals 1 to 11 of k. Sound okay? Got some nods, got some nods. And that is that. Anything else before we kind of sign off?
Mr. H, is the homework going to be on the hub?
Yes, I will put it on the hub in the next couple of minutes. Brandon looks like he has a question.
Yeah.
Sir.
Why would you add? Oh, because it distributes the negative. Okay. Yeah.
Exactly. Exactly. Okie dokie. Well then, I guess we're at that time. I will see you guys. We X'd on Friday, so we don't X this week. Do you guys know when your next test is? I think I have it up there on the hub.
May 19th.
May 19th. Okay. So a little bit more than a week. Sounds good. All right, guys. Have a good Monday. I hope you all passed Mother's Day. I just feel like it's kind of a test. Everyone pass? Everyone pass? Yes, yes, yes. No angry mothers. Okay, good. All right, people. I'll see you tomorrow. Have a good evening.
Thank you.
Thank you.
You're welcome.
Mr. Reeves.
Mr. Reeves.
Yes, yes, yes.
I can.
All right.
Okay. So I did like quick corrections for my test. Can I send that to you, or is it? Or
Yeah,
not?
please do.
Okay. Thank you.
We'll let you know how those look. And
All right. Will I be able to get some points back or no?
if we're not really one of the classes who kind of does that, but I will see. It can't hurt. It cannot hurt.
Okay.
I mean, that is for sure.
All right. I'll send it to you. Thank you, Mr. Reeves.
You bet.
See you.
Have a good one. Yes.
I did the wrong homework.
Oh, don't
I
worry
did the
about
homework
it.
that was on the assignment sheet on accident.
Okay.
But
Okay.
I submitted it in like the middle of class because I realized and I was like, so I resubmitted it and I was like, oh, I did the wrong homework. I
Okay.
like put that as a comment. So
Yeah, just fix it. I won't worry about it.
okay.
Okay.
Cool.
All right.
All right.
Thanks.
Thank
Bye.
you.